Yeah, welcome to another video tutorial session on finite element procedure for solving structural engineering problem. In this video session, I'm going to analyze this problem with ANSYS software, the ANSYS program. In my previous tutorial, I actually analyzed this problem using the penalty method on the MATLAB working environment. We determine the deformation at the node, the displacement at the three nodes of this truss. In that video session and in that tutorial session exercise, we also determine the axial force in the three members, and we determine the reaction component at the support reaction. In this video, I'm going to illustrate how we solve this problem on the ANSYS. This problem, I've actually analyzed a truss system on the ANSYS program before. So, but the main difference between that solution and this is this roller support found at node 3. So, how do we define the roller support, an inclined roller support at a node? So that is like the main learning objective of this lesson. We need to define a reaction component at this direction in the y prime direction as seen here. So we need to define a reaction at this, a support reaction in which the reaction is in the y prime direction. So I'm going to show you how this can be done on the ANSYS program. Before I move to the ANSYS program, I would like to define the definition. The truss has three elements. One element is 1 meter long between node 1 and node 2. Another one is 1 meter long between node 2 and node 3. And the third element between node 1 and node 3 is at 45 degrees from the positive horizontal axis. So we are using ANSYS to solve this problem. We have a point load. We have a point load at node 2 and 1000 kilonewton force at node 2. And we are given just beneath here that the cross-sectional area of all the elements is 6 times 10 minus 4 meters square. And the Young modulus for our material is 210 times 10 power 6 kilonewton per meter square, or 210 gigapascal. So I'm going to move to the ANSYS program now, so that we can solve this problem. I'm going to move to the ANSYS workbench. I am on the ANSYS workbench working environment now. So the first thing we need to do, we need to activate our static structural solver. So I'm dragging from the left hand side of the screen, drag and drop to the middle screen. We need to go through this workflow. So the first thing we need to do, we need to define our material property of our source, that is the Young modulus. So you double click on the engineering data. We are creating a new material. I always call it steel. You can give it any name you want. Call it steel. I will add the isotropic elasticity to the new material created, and I will define the Young modulus of that steel to be 210 gigapascal. First, I change the unit to gigapascal. I enter 210 as specified in the question. Young modulus E is 210 gigapascal. The portion ratio, let's assume it is 0.3. The portion ratio, as I always say, does not affect the accuracy of source elements when we are using the finite element procedure to solve structural engineering problem. It does not affect source problem. So what we can do now, we close this tab. We have defined the engineering data. Now the geometry. Before we double click on geometry, we need to click on this line body. Make sure this line body is checked, and you Then double click on the geometry to open this space claim working environment. This is where we define the geometric property of our source element. The space claim working environment is active now. So what we need to do, I always draw on the XY plane. So I'm going to select the XY plane. You do this by clicking the button down on your screen, sketch new, select new sketch plane. So you can select the plane you want. I select this plane, XY plane. I bring the plane to view by clicking this button, the plane view button. So once you have done this, we sketch um, our source geometry. From our question, our source geometry consists of three parts. The first part, element 1, is 1 meter at 90 degrees from the positive horizontal axis. The second part is 1 meter also. So I'm going to draw 1 meter line, another 1 meter line, and I'm going to connect it together. So essentially, I'm drawing a triangle to define my geometry. So I'll do that now. So click on this line button to sketch. So I'll start my sketch from the 0, coordinates of this XY plane. So I click on that point, enter 1000 mm. 1000 mm is 1 meter. So I'm entering, my unit is a millimeter. So that's 1000 mm. At 90 degrees, I'll draw another 1000 mm. And I'll connect the points together. As simple as that. So that defines the geometry. So what we need to do now, we need to create cross section. Click on the prepare tab, profile. Let's use a rectangular section to define our model. So I'm clicking on the rectangular cross profile. So we need to edit the dimension of the rectangular cross profile. So you edit the beam profile. I need to change the B and the H. So let's assume our cross profile is actually a square. And in our question, we are told that the cross-sectional area is 6 times 10 minus 4 meters squared. So what does this mean? If this is a square, what is the length? If this is our area and our cross-section is a square, so our length will be the square root of this value. So I'm going to use my calculator tool on my computer to compute the length of our square section. So 6 divided by 10,000 square root of it. So this is square root of it. But this is a meter. I need to convert to millimeter because I'm working in the unit of millimeter. So I have to multiply this by 1000. So this is my length for my cross section. So I'll copy this value and I will paste for my B and H. I paste this value here. Do the same thing for the other dimension, the H. So now I have a cross profile of 6 times 10 minus 4 meters squared, defined by this. So I'll close this window, click the structure button. We need to apply the cross profile to our line sketch. So under the beam panel here, click create and apply currently it's set to rectangle section, so we want to apply rectangle section to our line sketch. So I've clicked on the create button here. So you select the line you want to apply the profile to. So I'm selecting this line first. I do the same thing here and also do the same thing here. So I've applied our profile, the section to the three line bodies. So the next thing we need to do, come to the left hand side of your screen, you'll see three beams defined. You also need to press the escape button on your keyboard 2 times to leave the command. Select, select, select. You need to change the beam to truss type. So I want to change the three beam section to truss type element at the same time. So under the beam type, click on the drop down menu, select link truss. So they have been changed to truss elements. Before we leave here, we need to do one more thing. Click on design, share topology. You need to change the share topology from none to share. Very important. So once you have done this, we can leave the space clean working environment. We are done specifying the geometry of the model. So you close. Not closing. Okay, it has closed. So now I'm back to the ANSYS workbench working environment. So we've defined our geometry. We know this because the geometry is checked with the green check. So now we move into the model workflow. We double click on it to open the mechanical working environment. This is where we define our finite element model, we define the boundary condition, we define the structural load on its source, and we also analyze and view our results. So now where the mechanical working environment is active, so I would like us to click on this coordinate system, click on the Z arrow to bring the XY view to plane view. So if you check geometry, the geometry branch, we see one group of geometry specified. The group denotes the our three truss components. What do we need to do here? We need to actually assign our material to our truss element here. So with this truss group selected, come down to material assignment, change it from structural steel to steel. Steel is the material we created at the beginning of this video session. So once you have done that, uh, in this lesson, we need to create another coordinate system. Another coordinate system at the direction of our roller inclined support in the x prime y prime direction. We need to create this coordinate system and attach the coordinate system to node 3. So that's what I'm going to do in the mechanical work environment now. Now the coordinate system, I will right click, insert coordinate system. The geometry, I will click on this node here to assign geometry to that, to pick that node, to assign the coordinate system to that node. So I've created a coordinate system and I've attached it to this node. You can see the coordinate system at the node. So, but the coordinate system is not properly oriented, so we need to rotate it so that our x will point in the direction of this element, and our y will be normal to the direction of this green selected element. So how do we do that? With the coordinate system selected, I think what we need to do, we need to rotate the x-axis by 90 degrees. So click on this on the top of your screen, click on rotate Z. And when you click on rotate Z, on the left lower side of your screen, you will if you should scroll down, you will see rotate Z. because we click rotate Z. If you click rotate Y, you will also see the rotate Y at the bottom of your screen. So I want to change it from 0 to 90. So changing from 0 to 90 did not give the desired result. What of 180? I'm doing trial and error. So I don't think the rotation is for, we're supposed to rotate the X coordinate. So I think I will delete I'll delete this, I'll delete the rotate Z. I think we're supposed to rotate Y. So rotate Y 90 degree. Same problem. I'm working by trial and error. Say rotate ZX. Rotate X 90 degree. Oh, still same problem. It's not giving me what the result I want. I think it's rotate Z because that's what I used before. I think say minus 90. Okay, I just figured it out. We're supposed to actually not rotate, we're supposed to rotate Z, but not rotate it by 90 degree. We're supposed to actually rotate Z by 45 degree to get our desired result. So when I change rotate Z to 45 degree, the X coordinate is rotated by 45 degree, and we see our X pointing in the direction of this element, and our Y is perpendicular to this element. So I'm going to apply a roller support to act in the direction of this Y coordinate system. So that's why this coordinate system is important to be defined. Under the mesh, I have this element is 1 meter, 1000 mm. This is 1000 mm. This should be around 1.4 something. So I will define my element size as 1.5. 1.5 meters, that is 1500. Something greater than the actual source the actual length of the source element. So 1500. The element order, I'll use linear. It's quite adequate, but you can use quadratic if you want. No problem. So under the static structure, we define our support and we define our loads. So click on the static structure, insert. We click on displacement support. Displacement support was attached to this edge element. I'm going to change it. I'll click on this node here, geometry apply. So now the support has been applied to these nodes below. X and Y component is 0 as specified in the question. Let me show you. So at that node, we have a pin support 0, 0. At node 2, we have a roller support in the Y direction. So I'll only apply the displacement support in the Y direction. I'll leave my X direction free at node 2. So going back to mechanical, I will duplicate this displacement support and I will select this node, apply to geometry. X will be free, so I have to change this to free, and the Y is fixed 0. For this, I'll create another support because we have a inclined roller support at node 3. So I'll create another support for node 3, duplicate. I will select node 3 and apply that displacement support to node 3. So I want my Y to be fixed and my X to be free. But we need to change the coordinate definition from global coordinate system to coordinate system. Very important. So the Y component of that coordinate system is fixed, while the X coordinate is free to move. So that's how we define that support there. We can decide to group our support definition by selecting it and click group. We call this supports. not important, not relevant, but you can do this. So I'll now define my load, insert force. Only have one structural load for this model. So I'll select the node is at this node. So I'll select this node, apply, defined by component. The node is in the x direction, 1000 kilonewton, that is 1 million newton. 1, 2, 1, 2, 3. So, okay, yeah. Oh, 1, 2, 3, 1, 2, 3. In the x direction, the y and z, it is 0. So now I've defined the structural load. I can also put this load in a folder too. Just click on group, save forces. If there are many loads in your under this branch, you can group all the load in a folder, in a group. You name it anything you want to name it. So once I've done this, I want to go to the solution branch. I would like to add deformation in the x direction, deformation in the x direction, also deformation in the y direction. Deformation in the y direction, duplicate, change this to y direction, second one to y direction. So I'm doing deformation in the x and y direction using the global coordinate system. I might decide to actually visualize the deformation. If I want to know how this node move in the coordinate system I created in the x direction, I can choose the coordinate system. So let me do that too. Duplicate. I want to know the x movement at that node for the coordinate using the coordinate system I created. So also you can add easier force results for our solution. That's the solution branch. You can also add probe force reaction to know our reaction component at the support. So here I will click on displacement. You just need to select the displacement support where you want to determine the reaction. So displacement, I'll duplicate this result. Duplicate this result. I will change the boundary condition to displacement 2. I'll duplicate this result. I'll change the boundary condition to displacement 3. I think we can also group results under the solution branch. Yes, this will be my deformation results, displacement results, displacement results. This will be my force reaction results, support result, force reaction results, or support results, support reaction results. This is my area force. We only have one of it, but let me still group it. Source area force, source element area force. So now we can run our results to visualize the solution. Now the solution, the program has run and our solution branch is active. You can visualize our result. This direction deformation is the direction deformation for our truss problem in the x direction. The x movements of the movement of the truss member in the x along the x direction. So can see at let me use the probe. At this point we have 0, 0. The deformation at this node is 0. The deformation at this point, oh, it's not working. I need to zoom. Okay. The deformation at this node is 13.548. Deformation at this point is 5.612 mm in the x direction. If I should compare these results with my final element results on MATLAB, let's see. Deformation. So where can we find the results here? So this, I want this so I can select it. These two components are our deformation at node 1 in the x and y direction, and you can see it's a very, very small value, 0.003. Actually supposed to give us 0. MATLAB is actually giving us 0 for node 1 x deformation. For node 2 x deformation, this 3,4 is the xy deformation, 11.9 is the x deformation, 0 is the y deformation at node 2. The value here is 11.9052, and ANSYS is giving us 13.548, which is quite close. Finite element procedure is not an exact solution. It gives close answer to actual result. Actually, we don't know which one is actually correct because our MATLAB solution is based on finite element procedure. Also, the answer is also based on finite element procedure, but they are giving different solution. But the solutions are close, which is what is important. At node 3, we have 5.612. Comparing with the actual results, MATLAB, we have 3.9. 5 and 6 are the deformation is the movement of that joint at node 3. So in the x direction, we have 3.968, but MATLAB is giving us 5.612. This deformation result, I would say, is not bad, it's close, but I don't know which one is actually more accurate than the other. So this is the x color plots for the truss element. The y color plots, you can also probe the nodes. This should be 0. This should also be 0. But we should have a value here, 5.612, and we got 3.94 something in MATLAB. Say we want to find the deformation at this node along the x direction. So because I changed the coordinate system here to the new coordinate system we created, I can probe this node to determine the deformation in the x direction, in this direction. So the deformation is 7.9365 in that direction. So the node will move in that direction 7.9365 from its initial position, mm. So this is how we interpret our deformation result on the ANSYS program. The force reaction at this node, let me change this to tabular data, select tabular data, raise this up. Force reaction, the x component is 500 kilonewton, that is 500,000 newton, that's what we have here. And the y component is also minus 500 kilonewton, or minus 500,000 newton. So I think that's what we also have on the our MATLAB results. The reaction component, this is the reaction vector. which I calculated. This first two is the reaction component at node 1. You can see it's minus 5 times 10 to the power 3 and also minus 4.999 times 10 to the power 5. So this is exactly the same with our ANSYS results. Minus, both of them are minus, as we see here. For this reaction component at the second node, we have our value in the y direction to be a very small value actually, times 10 to the power 10, 1.0453 times 10 to the power 10. This should be like a very, very small value. As if there is no force in that direction. So this is like maybe 0.0001 Newton or something. We should check our MATLAB results. What do we have there? We have a very small value here, minus 0.0003. So if this is minus 0.003, MATLAB is giving us Newton. MATLAB is giving us 0.00001 Newton. So that's the result of this. No, this is minus 0.0. Here is actually minus 0.0003 times 10 to the power 5. See, very, very, very small value. So this should be minus 0.0001 times 10 to the power 5. So that is the interpretation of that result there. The reaction component at this point, we have minus 5 and minus 5. So we have minus 5 and minus 5 in the xy coordinate system. But say we want to find the reaction component along this y, along the y, along the support direction. The force should be 7.0711 times 10 to the power 5 Newton. But say we want to use another coordinate system to view these results. Let's see what we get. Let's run the result again. Yeah, we got a very good result in that y direction. You see, which is what we got in our resultant. And when we're using the global coordinate system, and see the y value is 7.07 times 10 to the power 5 Newton. This is a very, very small value, so this does not count. So the resultant can see is also equals to 7.0711 times 10 to the power 5 Newton. For the axial force, let's we could figure out the axial force in each element. Let's use the probe button. So I've clicked on the probe. Uncheck this snap button. So I'm selecting this. This is like a zero member. It's giving a very, very, very small force, 1.05 times 10 to the power 10 Newton. So this is giving us minus. This gives us minus 1,000 minus 1 million Newton or minus 1,000 kilonewton. Here it's giving us 707 kilonewton or 707,000 Newton. So this is the axial force in each of the member. So this is how we analyze problem like this with inclined roller supports on the ANSYS program. So I've come to the end of my video session today. In my next video, we're going to look at how we analyze a symmetric truss with symmetric loading. I'm going to explain this in my next video. I'm going to look at a symmetric truss problem with symmetric loading. How to reduce the symmetric geometry by half to get better results. It is said that when we reduce if there is a symmetry in our geometry and loading, and we take advantage of the symmetry by reducing our model by half, we get better results. So we are going to compare the results. We are going to compare full result of a symmetric model and the result of half model of that same symmetric problem. We are going to compare the result to see the difference in the output results from both model in my next video. Thank you so much for taking your time to watch my video. I hope you've learned one or two things. Have a great day.